Welcome to this extremely important topic of frequency response. We will define discrete time Fourier transform. We will discuss how the magnitude and phase are useful. We will define filters using frequency response. This is the Fourier transform pair that we obtained in the previous video. Remember, this small u is the time domain signal, continuous time. This capital U of f is the Fourier transform. This capital F is also a continuous variable. You have minus j times 2 pi ft here. Here you have plus j times 2 pi ft. Now let capital omega equals 2 pi f, capital F. When I substitute this here, df becomes d omega divided by 2 pi. So I get this expression for u of t. This u of t and this u omega expressions are Fourier transform pair. Now we will be interested in defining discrete time Fourier transform. Let us apply u of n equals exponential j omega n. This is my input to a system whose impulse response is g of n. We will call the resulting output as y. Using Euler's formula, we can see that exponential j omega n is cos omega n plus j times sin omega n. So through this expression, compact expression, we are applying a sinusoidal signal. We also say that we excite this system with sinusoids. So the output y is given by the convolution of gn and un, which is nothing but this very well known expression. We will keep encountering this throughout this course. So let us write this by substituting exponential j omega n in the place of un. Okay. So it is u of n minus k, wherever n occurs you put n minus k, j omega n minus k. Now let us pull out this j omega n, because it is a constant, we can pull it out. It is a constant given that n is fixed. Now we will define discrete time Fourier transform as follows. Whatever is inside this summation is defined as the discrete time Fourier transform. It is abbreviated as dt ft. Now I can write this as z to the power minus k with z at exponential j omega. Replace only the last term like this. What is the need to write like this? Do you recall what this denotes? This denotes nothing but the z transform, g of z. G of z when evaluated at z equals exponential j omega gives rise to this, which is defined as g of exponential j omega, and this is nothing but this particular expression. As a result, I can get yn equals exponential j omega n times, in the place of the summation I put g of exponential j omega. This is the important expression. We will study this in little more detail in the coming slides. We have to recall, of course, in order to use this z transform, we require that the sequence converges absolutely. In the next slide we will start with this expression. So here is that expression. How did we get this? We applied u of n equals exponential j omega n to a system whose impulse response is g of n and obtained the output y of n, and we obtained it through the convolution expression. And it is important to remember the same omega that you used in the input u appears in the output also. This omega and this omega are identical. You should never forget this. And the meaning of g of exponential j omega is given here. This is known as the frequency response. When we excite a system whose impulse response is g of n, we get the output exponential j omega n times this whole thing. Omega is the same. Whatever frequency you used in the input appears in the output also. This is an extremely important property of frequency response. Let us now write this in polar coordinates. I can write this expression g of exponential j omega as magnitude and phase. Why do I have magnitude and phase? Why is this complex? That is because I substitute exponential j omega in the place of z, and g is a polynomial in z. As a matter of fact, ratio of numerator and denominator polynomials, when I substitute in the place of z exponential j omega, which is a complex number, I get complex entity for g also. So now let us substitute for this g from here. So this is the magnitude, this is the phase. When I substitute this over here, I get this expression. Now I can group these phase together, I get this. Now recall that capital G of z is the z transform of g of n. Okay, now we want to consider the changes in magnitude and phase. We applied a sinusoid with frequency omega to Gn, and I obtained this output where capital G denotes the z transform of g of n. When input is a sinusoid, output also is a sinusoid with the following properties. The output amplitude gets multiplied by the magnitude of g of exponential j omega. So you can see that the magnitude gets multiplied by this magnitude of g, capital G, and output sinusoid shifts by a phase of phi with respect to the input. Of course, also remember the frequency remains the same. Whatever frequency you have in the input appears in the output also. What we are going to discuss in this slide is also extremely important. Frequency response defines filtering. Okay, this is the expression we had in the previous slide. At omega, where this magnitude is large, the sinusoid gets amplified. This becomes large, means the effect is felt in y of n at those frequencies. Wherever it is small, the sinusoid gets attenuated. The system means this system with impulse response g of n and the z transform g of z and discrete time Fourier transform g of exponential j omega. When the magnitude is large at low frequencies and small gains at high frequencies are called low pass filters. In other words, a low pass filter is one that has large gain for capital G of exponential j omega at high frequencies, that is large magnitudes at low frequencies, and small gains at high frequencies. So these are known as the low pass filters. Similarly, high pass filters reject low frequency information. They have small gains at low frequencies and large gains at high frequencies. Using the same idea, we can define band pass filters. They pass a particular frequency range. Only in that particular frequency range this magnitude will be large. At all other frequencies this magnitude will be small. We can also define other filters like notch filter and so on. With this, we have come to the end of this presentation. We will discuss this idea soon. Using this, we will define filters.